Aloha, Rich Halverson here. This is ITS228. And in this video, I'm going to try to get through the lab 7.11 on AVL trees. So if I share my screen, I'll just start with a little discussion. It's this chapter. An AVL tree is a binary search tree that's balanced, that's height balanced. That means a height balanced tree just means that the height of the left subtree differs from the height of the right subtree by at most one. Okay, so it's either going to be 1, 0, or -1. So it's this balance factor thing. And of course, that makes it more likely that any search for something, a search for a key in the balance in the BST will be O of log n, which is what, ideally. So the tree's not going to be all skewed and everything. So the thing about these, to maintain the balance, is you have to have some methods to rebalance the tree. So whenever you insert or you delete, you got to rebalance the tree. And there's two kinds of AVL trees. There's AVL, and the difference has to do with how the balancing works. The definition of balanced slightly different, and how the balancing is done, the methods for doing the rebalancing. And so there are AVL trees, and by the way, AVL is just the name of the people that came up with the idea. I don't remember what it stands for. You can look it up. What does AVL stand for? No. AVL tree. Adelson, Velsky, and Landis. All right. So anyway, all right. So now in this, okay, and so the way an AVL tree keeps track of its so in the node, in the root of an AVL tree, or the parent or whatever, the node of an AVL tree, the root of an AVL tree, it contains a property that remembers its height. And so rebalancing is just, calling asking for the height of your left subtree and the height of your right subtree, and seeing if they're the same, so on. All right, so all right, but in this problem, we are going to do instead of an AVL tree makes it easy, of course, to find a key in log n time. But what we're going to look for, what we're going to do is we're going to modify the AVL tree. So instead of finding a particular key, we're going to find the nth largest key, or the nth largest key. Yeah. So you can imagine doing an in-order search. The brute force way to do this is you want to find the 5th largest key. So you start to do an in-order search and you stop after you hit 5. Or if you want to find if the tree's got 10 million nodes in it, it's a balanced binary tree. It's got 10 million nodes in it, which means to find the millionth largest out of a 10 million large tree takes a million comparisons, or you have to traverse the tree a million times, do an in-order search and go a million until you find the millionth item. So we're going to modify the AVL tree to keep track of the number of nodes in your left branch and in your left subtree, and the number of nodes in your right subtree. And using that, we're going to be able to modify it so we can find the nth largest in log n time. Okay, isn't that cool? All right, so they give you code for regular BST node and binary search tree, and they also give you code to do the AVL tree modifications. So it does the rebalancing, the AVL tree rebalancing. That's the tough part. It's when you delete a node in an AVL tree that a lot of stuff has to happen because of all kinds of rebalancing down below, and you got to rebalance the whole thing because it might be smaller. So they give you that, and then what they tell you to do is they tell you how to we're gonna our task is to do the extended AVL tree. Okay, so to first of all, we have to add this method which is going to do the subtree key count. Number of keys in the subtree are same as the number of nodes in the subtree. Okay, so like for example, this node here, this is the root of the tree. There are 7 nodes in this tree. Okay, 1, 2, 3, 4, 5, 6, 7. There are 2 nodes in this subtree. 1, 2. There are 4 nodes in this subtree. 1, 2, 3, 4. And so, of course, once the number of once these values are known in your subtrees, then to figure out how many nodes are in yours U as a tree, it's just your left subtree plus your right subtree plus yourself. So let's start implementing the extended AVL tree. So we should take a look at. I wrote down some notes here. It's important. Okay, so let's take a look at first BST node. This is the basic. This is the node. It starts with BST node. It's got a key. It's got a left subtree. It's got a right subtree. And it's got a parent. Okay, and there's methods here to get the key, to get the parent, to get the left node, to get the right subtree, and then there's this subtree key count that we're gonna have to write. Or it's just there. We're gonna have to write it, and we're gonna write it in inheriting class. We're not gonna write it here. We're gonna write it like in here. Okay. So this is and then it gives you some methods if you want to replace a child with some other child. If you want, and of course that would if you want to set a new key value, set a new left child, set a parent to null, set a right child, and so on. Okay, so those are all given to you, and then let's take a look at how it's extended for AVL node. So we have with this class it inherits everything from BST node, and then you see when it initializes, it just uses the BST node initializer, and then it sets a height. AVL tree has a height, right? Keeps track of its height. That way it keeps it. Then if the heights in its 2 children differ by more than 1, it's going to have to do some it rebalances. So this will return the height of the left child. This returns the height of the right child. This finds out what the balance is. It's got to be -1, 0, or 1. This gets your own height. Gets your left sibling. No, just it gets your left subtree, gets your right subtree, sets your left, sets your right. These are all, we're just using the same ones that are in. See, this is the super is referring to BST node, and this just says use the set left method in the BST node. So this is going to be exactly the same as this set left. All right, so we see that AVL node, the only difference in AVL, it uses all the ones, but it's got has this update the height, and that's simply getting the height of the left tree and getting rid of the right tree, and so on. And It's the maximum of the left tree and the right tree. Anyway, so that's the important thing with AVL node is the only thing that's added is the height. Okay, now in extended AVL node, we have to add the subtree count. Okay, we have to add the subtree count to the AVL node. Now let's look at the let's also look at binary BS. Find this one. This is one that they give you, binary search tree, and this is here. This is a class binary search tree, and you can do an in order search. You can this does an in order traversal. It does insert key. It does remove key. These are insert nodes, remove nodes, search for a desired key, find out if it's in there, insert a node. Oh, oh yeah, okay, so this inserts a new key. This inserts a whole tree, I guess. This would be inserting a whole tree if you want to insert a tree, a subtree. Make a new node, remove a node, and rotate. Oh, these are, you don't really have to, you learn about these up in the text, and rotating left has to do with if something is imbalanced and you have to, when you're removing and you're replacing, you have to sometimes you have to rotate the tree, and you learn about that up above, but you don't really have to understand it to do this problem. So anyway, that's a binary search tree. If you look at is get nth key, yeah, this is what we have to this is what we're going to end up implementing. This is just there, I think, so this runs when you execute it, but we're going to have to write this okay. We see that yeah, I just talked subtree count will be used to get, yeah, the subtree count in extended AVL tree. I guess we have to add that extended AVL has to finish. We have to finish that subtree. And where's get nth key? Is that? Oh, this. All right. Anyway, so let's get started. We have to write code. You notice this one is not. All of these are read only. Main BST node is read only. AVL node is read only. Extended AVL node is not read only. We got an added code here. And binary search tree is read only. AVL tree is read only. Extended AVL tree is not read only. We have to add code here. We add code here. We add code here. And the rest of these are all read only. Okay, so if we start with let's see, let's start with the AVL tree. Which subtree is modified? Whenever a subtree is modified, the node count must be updated. Okay, so let's start with, I guess, AVL node. Extended AVL node. Let's see, extended AVL node is here. And okay, so return. Okay, now we're going to add additional code. Now, let's see. Should I start with an extended AVL code? Get left, get right. I'm going to start by adding a update. Let's see. Let me go to I'm trying to decide which one to start with, so it makes sense to you. All right, so in extended AVL node, we're going to be using some of the AVL node and I think AVL node and some of the AVL node methods directly. And so we're going to have to put references to those methods in extended AVL node. I'm going to go to I'm gonna go to extended AVL tree here, and I'm gonna start writing code right here. Make a new node, and we have an extended. We have all right, I'm gonna put rebalance get nth key. There it is. Okay. So first of all, I'm gonna put insert node def insert node. We're gonna have to have this and self node. This is the node that comes in, and this AVL insertion starts with just the standard BSD. Okay, so when this is the extended one. So when we insert a new node, first we're just going to do the AVL insert, but then we have to add to it the node count. The node count. Remember this. So the extended AVL tree, the nodes, the tree also it not only remembers the height, which it needs to for AVL tree, but it also remembers the node count, which it needs for this extended AVL tree. So when we insert the node, first of all, we're going to just do the insert node of the parent of the class from which we are inheriting this, which is this from this class. This is the super class here when we refer to super down here. So node. So we're going to use the super class. The super class's insert node, and then we have to get the we have to figure out what we have to update. We have to add the subtree count. Okay, so let's get the parent. I'm going to call it parent node equals the node that we just inserted, get the parent. And then I'm going to, so that I know. I insert this node, and then I've got to update the node count for all of the nodes all the way up to the root. Okay, because all of the node counts for all of the parents, all the ancestors have to be incremented by 1 because we're adding 1. It's going to go away. I got this. I did that 2 days ago, and it's supposed to fall off. I hope it falls off before I make my next video. All right, so that's so we have to get the parent node, and I'm going to say while there is a parent node, we want to update the node count, or update the key count parent node dot update subtree, and we're calling it subtree key count. And then we got to keep on going up. So it's parent node equals parent node dot get parent. So we keep on going up until there's no more parent. And each time we go up a parent, we're going to update the tree count, the subtree count at that parent. Okay. And then we've just inserted something, and so we should now we have to rebalance. So I'm gonna get the parent again. I'm gonna say just node equals node dot parent, get parent. And we're gonna, while there is a node, we wanna self rebalance. And then we wanna go up one more, node equals node get here. All right, so now I am not, what happens with when we do the insert node? You know, this is my solution. I mean, this insert node is the AVL trees insert node, but that the AVL's insert node should do this rebalancing. It's fine. Yeah, the AVL. Oh, where's the AVL insert? Is it in here? It must be in here. Okay, so it doesn't do the rebalancing. Well, I don't know. Maybe. Okay. Anyway, so let's keep moving here. And so I'm still working on this tree. All right. So we've got a new insert here to insert the when we insert a node into the tree, we have to we have to update the subtree counts all the way up the line because it's going to change. You're going to add one to them probably, and then you're going to it seems like it does seem like the okay, anyway, it seems like if you rebalance it, it's going to mess up the it seems like when you rebalance, it's going to mess up the height, the subtree counts. But it turns out that when we do rebalance, rebalance is going to be self-rebalance. Self-rebalance. So we're going to define our own rebalance here. Def rebalance is a self node, and we're going to rebalance this node. And to rebalance it, we're going to first. Oh, to rebalance it, all we do is we call the nodes update subtree key count. Update subtree key count. First, we're going to update the key count. Yes, that's the number of nodes. Then we're going to rebalance it. Return super rebalance. Call AVL trees rebalance. Did I not look at the right place? I didn't look in the right place, did I? Rebalance, this is it. Okay, there we go. And rebalance, checks rebalance, does rebalance. Okay. All right, so before I was looking in the wrong place. Okay, let's go back to this. And so this takes this does the key count, and then it does rebalances. And let's and now we can put this code in here, and let's write this code. The current node is the root of this AVL tree. And you know, I'm not going to write this now. I'm going to write this later. Okay, so we have to make sure we have the rebalancing. No, we have to make sure we have the update subtree count working, and that is in the extended It's in this one, extended AVL node. So let's go over to extended AVL node. And we're going to start by, we're going to have to get subtree count. That's that. Okay. Yeah, get nth key is what we're going to. Okay, so get subtree count just returns the subtree count, and then we're gonna need to use a get left. Is that right? Let me see. Set left, get left. I'm gonna write the update subtree count. Update def. Oops. Def update subtree count. Subtree key. Update subtree key count. Is this even spelled correctly? Okay. That's not in there. Okay, so let me go back to here. Update subtree key count of self. We're going to get the new count. We're going to start out with 1 because we count ourselves. And then we're going to add the left. The left. We have to get the left child. Let's get a handle on the left child. And let's get the right child. Let's get something like this. Right child. And if there is a left child, then we're going to add the subtree count of the left child. New count. Add to that the left child subtree key count. And if there's a right child, then we're going to add the right child subtree key count. All right. And then so then we can set, once we know the new count, we can set self subtree key count equals this new count. All right, so that's updating the C count. Now, so we need to be able to we need to have a get left and we need to have a get right. I think that's all we need. So for get left, let's just put it up here. Def get left self is simply super return super get left. And def get right of self is simply return super get right. And why do we need set? I know why we need set because, oh, I know why we have to overwrite set, don't we? Because set might change. Well, let's see. Extended AVL tree. Insert get parent. All right, so we've filled this in, but I have in my notes, we need a set left and a set right. Oh, oh yeah, because it would affect the key count, right? If we're setting a left child or a right child, then we are then the key count of that node is going to change. Well, we don't know what the key count is, and then of course it's going to change the key count all above. So yes, we do need to have our own. We do need to override the set left to child, and we need to, and that's just going to be the super set left to left child. And then after that, we have to update the subtree count. And we should do the same thing for the right. Step left. Step left. Self new. Set left. Set left. This should be self. And this should be self. New right child. And first we do the super set right new right child. Then we self update. Subtree key. Okay, so that's puts that in there. So I think we've done everything except for the implementing this. And so we should be able to run this. I guess I'll put this data in there. I'm not sure what this does, but so I'm going to put this data in here and I'm going to run it in development, see what happens. Probably get syntax error. Ooh, okay. So it looks like runtime error while executing test case. All three of them failed. And what we're trying to do is we're trying to insert remove, insert remove. And runtime error. Oh, I see. There was a runtime error. Oh, well, that just means there was a probably a syntax error. So let me. It would be in either extended AVL node. So let me see what this looks like. Let's see if the error is. It doesn't tell me where the error is. Init, get subtree key count, get left self super, get left, get right self return super, get right, set left, new left child, set left, left child, self set right, self new right child, set right new right child, update that, and when we come to here, it's start with the new count, get the left child, get the right child. If there's a left, add it to the new count. There's a right, add it to the new count. Then we're done. Let me go over to the tree. I didn't finish that, but I think that should matter yet. Let me go over to the tree. And we have this insert node as superinsert. Okay, that node. Well, that node. Update the subtree count. Get the next parent. And then set node to the node's parent. While there's a node, rebalance, get the parent. Rebalances. Update subtree key count. And rebalance. Let's see if that fixed it. But that fixed it. Okay, great. So it passed all those tests, and now it just didn't do the get nth key. It didn't pass that. Okay, so we're part of the way through. And so let's write this get nth key. And so to do that, we're going to kind of do a binary search. We know if we're looking for the 10th key, and there are and we look down the left, our left child. Let's say we're looking for the 10th key. We look down our left child. It's seven nodes down there. We know it's going to be down the right child, right? So we go down the right child, and we figure out, based on, we've got 7 already, and we need 3 more. So based on the children of the right child, those children, it's going to be, you're either going to go down to the left or the right, and we can try to code that. So we start at the root, and while there is a current node, we're going to say that if n equals 0 to n equals the left subtree key count minus 1 are keys in the left subtree, and n equals left subtree key count is the key in the current node. That's right. So if the one we're looking for is equal to if it's 10th, and there's 10, the left subtree key count is 10, then we know that we are actually at the node that we want. We're at the index that we want. And if n is greater than the left subtree key count, n greater than are the keys in the right subtree. So that's basically what's going on here. And so we can start by saying the self left child, let's say the left child is equal to the current node dot get left, and the self right child is equal to the current node get right, and the left count Write it this way. If self left child exists, then left count equals self left child left child get subtree key count left count is equal to the key count of the left child. That's the left count. And if n is less than the left count, then the current node is equal to the self.left child. Otherwise, if n is equal to left count or not self right child, then we're going to return current node. We're going to return the key of the current node. Otherwise, the current node is equal to the right child. And n is equal to n minus the left count plus 1. You can think about that. And so it's either going to go through until it returns, or if it makes it all the way to the end and there's no more nodes, then it's just going to return 0 because there isn't one. All right, let's see what this does when I run it. Still failed the last one. I wonder what it didn't like. Let's see. So let me go look through this code again. Current node is self get root. There was no syntax errors. Self left child is current node get left. Right is current node get right. Left count. I forgot. Oh, that's left count is equal to self. Otherwise, it's 0. Oh, if self, I forgot the else 0. I see that I got this spelled wrong here. And now when I run the program, I pass all the tests. And when I submit it, it looks like I got all the points. All right, well, that might not have been that clear, but I hope this helps. Thanks for watching.